So the G8 gift was this little dissection puzzle. It's two colors. Let's see, are they on the screen now? Yeah, there's two colors across four shapes. The shapes were acute triangle, scaling triangle, almost triangle, and generic quadrilateral. Problem 1, use one of each shape to make an equilateral triangle. Problem 2, use all 8 to make a perfect square. So a lot of people spaz around matching up edges. That's not very successful. What you want to do is you want to identify the 60-degree vertices of the equilateral triangle to solve problem 1. Now, suppose you were trying to just use these pieces to illustrate the theorem that the vertex angles of a triangle add up to pi, the straight angle. Now, it would appear that we don't have enough triangles. If we had 3 sets or another set, then we could plug an upside-down triangle and do this. It turns out, among these pieces, the middle angle of each triangle is matched by some angle in the quadrilaterals. So, for instance, here, we can see that one matches that, and those, of course, already match because they're congruent. So if we plug this in here, we're going to get a straight angle. Now, are these the 60-degree angles we're looking for? No way. This is not equal to this because this isn't equal to that. And so the reason is that the ones that are equal are this, this, and this. So we could just do this and see if that's a straight angle. And whoopee it is. Are those our angles? No, because we're not allowed to use 2 of the same piece. We're only allowed to use 1 each. So what we've got to do is find among the quadrilaterals a 60-degree angle. And in fact, it's this little thing right here. Now we've got a thing pretty well nailed. And first, I got to admit that I'm sort of lying to you. This puzzle is 8 times harder than I'm letting on because the puzzle that I gave out was, I didn't tell you which side to peel. Okay, so there's all that there's all those flip ambiguities. So anyway, here's the pieces that we need for the corners or for the vertices. And where was well, we can use this for the apex, and we can put this here, and then I guess we should put that guy out there. And of course, now you can just see the answer, like so. And now, for reasons that will soon become clear, I want to just copy this. That's the answer to problem 1. Okay, so let's make another one of those, like so, and like so. And of course, this one is going to have the colors reversed, like so, and like so. And about 5 years ago, a very young Neil Bickford, oops, I got this thing a little cocky there. So it was 6 ways to do that, 5 ways to do that wrong. So about 5 years ago, a very young Neil Bickford found this solution probably quicker than I just showed you. And then he immediately did this hinging transformation, which he referred to as a hinging transformation, which kind of weirded me out. And it's this operation right here. And then if I can just do this more convincingly, like so, there we've got a magic isosceles right triangle, and all we have to do is do that twice, and the problem is solved. But that's just not sexy enough. So I just wanted to, before we proceed, point out this interesting homology here. Black triangle, white triangle, white triangle, black quad, white quad, and yet they're all switched somehow. So instead of doing the logical thing and hinging this one, I'm going to hinge this one again. And it turns out hinging is an involution, which means hinging equals unhinging, which sounds a little odd, but now we've got this guy back. Okay, and what do we want to do with it? Well, it turns out we want to turn him upside down, like so, and slam him up against this thing, making a rhombus. And we're going to argue that, well, this could be progress because we're trying to make a square, and we've got 4 sides equal, so why not? So let's just, there's a crack of symmetry. Let's try to do something with that crack of symmetry, like switch these 2 halves. Whoops, there we go, like so, and like so. And if we do that, we've still got a rhombus, but it's a slightly squarer one. And at this point, you might just be able to see what's going to happen next. Another crack of symmetry, and we can just do this, And there is the color-sorted square solution. And then when we're done, am I over already? Okay, so we can hinge this again just for completeness. All right, and well, maybe not. Okay, so and I'm really glad I'm out of time because I've got to get this tabletop back to my room before the hotel notices it's missing.
Very nice. Very nice. That's